Hello everyone. In the third part of my mini course, I'm going to describe or try to get the Schrödinger-Lishnerovitz formula for the Dirac operator. So part number 3, the Schrödinger-Lishnerovitz formula. So first of all, before we start, I would just give a quick reminder. Yesterday we have seen that a Dirac bundle is given by a complex vector bundle with a connection, a Hermitian metric, and what we call gamma, a linear map that satisfies three conditions, 1, 2, and 3. And there are compatibility relation between nabla and the Hermitian's metric, as well as gamma and nabla, given by the condition 1, 2, 3. And the complex vector bundle sigma m is a rank L, but when L is the complex rank is 2, the integer part of n over 2, we say that M is spin C, your Riemannian manifold or your oriented manifold is spin C, and one can define the Dirac operator to be gamma Ej, nabla Ej, j from 1 to n, and of course the D, called the Dirac operator, acts on sections of the complex vector bundle sigma of M, which are called the spinor fields, and sigma M is called the spin C bundle or the spinor bundle. And of course we have seen that we need condition 1 and 2 to prove that it's formally self-adjoint with respect to the L2 scalar product, and also we have seen that we need condition 2 and 3 to prove that d squared and the Laplacian have the same principal symbols. So today I'm going to proceed. I'm going to talk a bit about this Dirac operator on my Riemannian manifold. So from now on, I'm going to assume that my manifold is spin C, so I can define the Dirac operator. I have my complex vector bundle, and I have what we call the Clifford multiplication, gamma. So my next proposition is about the Levi-Civita spin C connection. So I have a Riemannian manifold spin C, so automatically you have the good Dirac bundle with the rank 2 to integer part of n over 2, and I can define the Dirac operator for sure. So for every x in gamma Tm, for every tangent vector, and for every local spinor field, psi. So I'm going to work now on some open U of my manifold. So that's the spinor field. It's locally at the point. I'm working locally on my open U. We have nabla x psi equal 1 over 4 sigma j from 1 to n, gamma Ej, gamma nabla x Ej of psi plus I over 2 alpha of x psi, where I alpha from Tu to IR is an imaginary local one form, and it is it is a local expression of the connection on the auxiliary line bundle L. So if you remember this auxiliary line bundle L, so this is the depth of sigma of n to the power 2 integer part of n over 2 minus 1. We have proved that such a power exists, and we have proved also, or we have seen yesterday, when the auxiliary line bundle is trivial, you have the spin structure. We say that you have a spin structure. And then for people familiar with spinorial geometry, when you have a spin manifold, so the following extra term will not appear in my spin C connection or my formula for the spinorial connection. So here I have the spinorial connection. We call it the spin C, the Levi-Civita spin C connection. Maybe you can see why, because I can relate it to the Levi-Civita connection of my Riemannian manifold, plus the following extra term, again, that it is zero when you have a spin manifold, of course, because when you have a spin manifold, your auxiliary line bundle is trivial. So you take the trivial connection, okay, and whose curvature is zero, so the following term will not appear. So that's what we call the Levi-Civita spin C connection, and that's how we relate the spin C connection to the Levi-Civita connection. In the next step, I'm going to prove the following identity. So next step, the proof. We need to prove. So I'm going to write it one more time. We need to prove that the spinorial connection or the spin C connection locally, it's given by sigma j from 1 to n, gamma ej, gamma nabla x ej psi plus I over 2 alpha of x psi. Of course, so what I'm going to do, I'm going to denote nabla x0 psi, the following quantity in red here, and we can easily check that nabla 0 satisfies also the condition 2. It's a simple exercise. It means we can easily check that nabla x0 satisfies the following. Nabla x0 of gamma y psi is gamma nabla xy psi plus gamma y nabla x0 of psi. So this is left as a simple exercise. So then I'm going to denote nabla x minus nabla x0 by nabla prime x, and because nabla and nabla 0 both satisfies a condition 2, then nabla prime x of gamma y psi will satisfy its gamma y nabla prime x psi. Hence, nabla prime commutes with gamma txm for every point x in U, of course, in my open set. And so it also commutes with gamma cl of txm. So this is the extension of the Clifford multiplication from the tangent bundle to the Clifford bundle for all x, of course, in U. But, so we have nabla prime, it commutes now with gamma of CLTXM, but nabla prime X is an element of the endomorphism of sigma XM, and since it commutes with endomorphism of sigma xm. Why it commutes with the endomorphism of sigma xm? Because it is a subset of gamma CLTXM, and since it commutes with this guy in yellow, so it commutes with endomorphism sigma xm. So nabla prime commute with the endomorphism of sigma of xm, and hence nabla prime x is in the center of the endomorphism of sigma xm, which is trivial. The center of the endomorphism is trivial. What does it mean that nabla prime x is in the center and the center is trivial? Then on U there exists a complex one form. I'm going to denote it by beta, such that nabla prime x is equal beta x by the identity, again because the center is trivial. So now we equip the auxiliary line bundle one more time, which is the determinant of sigma m to the power 2 integer part 1 minus the integer part of n over 2, with the connection induced from nabla on sigma of m, and locally we have just a simple calculation. So what do we have? This is a connection I alpha of x. This is a connection, the local expression, or the connection, the imaginary one form that is the connection of the auxiliary line bundle L. But this is 2 1 minus n over 2 nabla x of that sigma of m, because we equip L with the connection induced from sigma of m. But this is 2 1 minus n over 2, by definition nabla x, that of sigma of m, which is a complex line bundle. This is the trace of nabla of x, which is 2 1 minus n over 2, the trace of we have nabla of x is now nabla x0 plus beta of x identity, which is nabla x0 plus nabla prime, of course. But we have proved that nabla prime of x is beta of x identity, and this is 2 1 minus n over 2. Of course, the trace of nabla x0 is 0, because nabla x0 is traceless. So I still have 2 to the power n over 2 and beta of x, which is 2 beta of x. So as a conclusion, what we will get, so conclusion, nabla prime x is nabla x minus nabla x0, but nabla x prime, we have proved that is beta of x by the identity, and we have proved that beta of x is I over 2 alpha of x times identity. So in conclusion, the spinorial connection is given by nabla x of psi is I over 2 alpha of x identity plus nabla x c. And that's what the desired result, or what we wanted to prove. So I had added the psi here, so I should make it clear by adding psi here and adding psi here. This is the local formula, or the local expression of the Leash-Civita spin C connection. And again, in the particular case, when you have a spin structure, there is no term, or the term I over 2 alpha of x is not here anymore. It disappears, because in the spin case, the auxiliary line bundle is trivial, and we equip then the complex line bundle, the auxiliary line bundle, with my trivial connection, of course, whose curvature is 0. So now we have related the Leash-Civita, Riemannian Leash-Civita connection with the spinorial Leash-Civita connection, and now I can give the formula, or the Schrödinger-Lishnarovitz formula. This will be my next proposition or theorem. Schrödinger formula. So you have a manifold, the Riemannian manifold, of course, is spin C. Then d squared, the square of the Dirac operator at the Laplacian, plus 1 over 4 the scalar curvature, plus I over 2 gamma of omega, where I omega is the curvature to form on the auxiliary line bundle. So we have denoted the connection on the auxiliary line bundle by I alpha. So this is ID alpha is the curvature to form on L. It's an imaginary global to form. And of course you are asking what is gamma of omega, and gamma of omega is the extension of gamma to forms. Normally we let the Clifford multiplication gamma, we always apply the Clifford multiplication to tangent vector, but now I can extend it to forms by, in particular to two forms, x wedge y, it's gamma x, gamma y, for all x, y, tm. So that's the composition of the two Clifford multiplication, gamma x and gamma y. So it means when you apply gamma of a form, of a x wedge y, of a two form, applied to psi, a spinor field, it's gamma x of gamma y applied to psi. So before proving the Schrödinger-Lishnarovitz formula, I would like to give few remarks. Of course, when you are in the spin case, because you equip the trivial line bundle with the auxiliary line bundle, with the trivial connection, so the curvature, the curvature of the trivial line bundle equipped with the trivial connection is 0. So you have d squared equal Laplacian plus 1 over 4, the scalar curvature of the manifold. Now I would like to come back to my first presentation, or to my first session on Monday, when we tried to construct a Dirac operator on Rn. And as you can see, you know that on Rn the scalar curvature is 0. Of course, and you get d squared equal automatically the Laplacian. So the idea, it really comes from my introduction on Monday. That's how you define the square root of the Laplacian or Rn. But of course, when you have a Riemannian manifold, it will depend on the geometry of the manifold, and more precisely, it will depend on the scalar curvature of the manifolds, which means the geometry of the manifold, plus one extra term, I gamma of omega, which means it depends on the geometry of the auxiliary line bundle. So just imagine that these two terms are 0, like in the case of Rn, because Rn is spin, so this term is 0, and the scalar curvature of Rn is 0, then you get the square root of the Laplacian. So that's the Schrödinger formula. It relates the Dirac operator to the geometry of the manifold, and as well the geometry of the auxiliary line bundle, defining the spin-C structure. So I'm going to prove the Schrödinger-Lifshitz formula in detail. It's very important. So let's do the proof. So I'm going to recall the local expression of the spinorial connection. It's nabla 0 x psi plus I over 2 alpha x psi. And we know also the local expression of nabla x 0 psi, which is 1 over 4 sigma j from 1 to n gamma ej gamma nabla x ej psi, plus of course I over 2 alpha x psi. We have proved this expression in the previous proposition, and now one can calculate the spinorial curvature Rxy applied to psi, and this is R0 xy of psi, where R0 is the curvature associated with the connection nabla 0 of x, plus the curvature associated with the connection I over 2 alpha, which is I over 2 omega xy of psi. And of course, because we know the local expression of nabla x0 psi, one can calculate R0 of xy, and it's easy to find that R0 of xy is 1 over 4 sigma ij from 1 to n, the Riemannian curvature of xy, R of xy applied to ei ej, gamma ei, gamma ej of psi, and of course plus this term I over 2 omega xy of psi. So it's easy to calculate R0 because we know the expression of nabla x0. And hence, if you remember, yesterday we have proved that the d square and the Laplacian have the same principal symbol, and we have proved that d square is the Laplacian plus 1 over 2 sigma ij from 1 to n gamma ei gamma ej, the curvature, the spinorial curvature ei ej. And of course now I'm going to replace r ei ej by R0 ei ej with this expression plus I over 2 omega x ei ej. So let's do it, and we already know the local expression of R0 ei ej. So what we will get the following: d squared, the Laplacian, plus 1 over 2 sigma ij from 1 to n gamma ei gamma ej R0 ei ej plus I over 4 sigma ij from 1 to n omega ei ej gamma ei gamma ej. And of course, to prove the Schrodinger formula, the Schrodinger-Lishnerovitz formula, we expect that the first quantity here in blue, that I'm going to call it quantity 1, should be 1/4 the scalar curvature of the manifold, and the second quantity in blue that I'm going to denote by quantity 2 will be I/2 the Clifford multiplication of omega with psi. So my goal now is to prove that the quantity 1 is 1/4 the scalar curvature, and the quantity 2 is I/2 the Clifford multiplication of the 2 form omega with psi. To do so, I'm going to calculate explicitly quantity 1, and then later on explicitly quantity 2. So let's try to calculate quantity 1. So because I need to calculate quantity 1, I prefer to already write my own calculation, show it to you on my screen, and then we can explain everything. So this is quantity 1. Yes, and in order to calculate quantity 1, I'm going to replace R0 by its expression, R0 ei ej. So to get 1/8 sigma ijkl goes from 1 to n. The component rijkl of the Riemann curvature, gamma ei, gamma ej, gamma ek, gamma el, psi. And now check the next step, because gamma ei, gamma ej, gamma ek is equal to gamma e. You can commute them in the order you want, like this: gamma ek, gamma ej, gamma ei, as you wish, if the I is not equal to j, is not equal to k. And this comes from the property 3 of the Clifford multiplication, which is gamma x, gamma y plus gamma y, gamma x is -2, the scalar product of xy. So that's why I'm going to divide this sum here in red into several parts. The first one, or the first step, what I'm going to do is I'm going to isolate gamma EL, the Clifford multiplication of EL. So what I still have inside my sum is the following. So no more gamma EL. So I'm going to play with gamma EI, gamma EJ, and gamma EK. First of all, this is where it comes 1/3 here, because as I said, gamma EI, gamma EJ, gamma EK, you can commute each two without any problem if I is different than J, different than K. That's why you have 1/3 Rijkl or JKIL plus RKIJL, gamma EI, gamma EJ, gamma EK. And then you still have the other two cases, is when I is equal, when K is equal to I, and this here. And the last case is when K is equal to J, and the last part of this summation. So you get Rijil, gamma EI, gamma EJ, gamma EI, plus Rijjl, gamma EI, gamma EJ, gamma EJ, and of course I have isolated the gamma of EL, so this term here is for the whole 1/8 summation from here into here. And of course, we all of us know the Bianchi identity, so we know that this term is 0 here, so this term will not anymore appear. And now for the next two summation, Rijil, so as you can see, Ijil, this is the Ricci curvature here, and Ijjl is also the Ricci curvature of EIEL, and the first one is for EJEL. So I'm going to replace this summation by minus the Ricci EJEL gamma EL EJ, and minus minus Ricci EI, gamma EI, gamma EL, where of course here I'm going to write it in yellow. I can use that gamma EJ is minus 1, and gamma EI is minus 1. After commuting it with gamma EJ, it adds another minus, so you get the plus. So that's where the Ricci curvature will appear, and then you can add both terms here to get minus 1 over 4 Ricci EI EJ gamma EI EJ. One more time, using the property 3 of the Clifford multiplication, which means gamma EI gamma EJ is minus 1 if EI is equal to EJ, and gamma EI gamma EJ is minus gamma EJ EI, but the Ricci tensor is symmetric, so if I is different than J, all this quantity is 0, so I still have only the quantity where I is equal to J, and I get the scalar curvature. So the quantity 1 is in fact 1 over 4 the scalar curvature of my manifold. And now I have to calculate the second quantity, the quantity 2. But quantity 2 is I over 4 sigma kj from 1 to n omega ek ej gamma ek gamma ej. But one more time, we know that if k is equal to ej, then this is minus 1, but in this case this term will be 0, so I can write it I over 2 sigma k strictly less than j omega ek ej. Don't forget, is omega is not symmetric, is skew symmetric or anti-symmetric, gamma ek gamma ej. And this is the definition of the extension of the Clifford multiplication to differential two forms. This is the Clifford multiplication of omega applied to psi. So I have proved that quantity number 2 is in fact the Clifford multiplication of the curvature 2 form of my auxiliary line bundle with psi, and the first quantity is 1 over 4 scalar curvature. Conclusion: t squared, the Laplacian, plus 1 over 4 scalar curvature of my manifold, plus I over 2 the Clifford multiplication of the curvature 2 form applied to any spinor field. If you would like to take any spinor field psi here, so 1 over 4 scalar of the manifold psi, and the Clifford multiplication of my curvature 2 form with psi. Okay, so after establishing the Schrödinger-Lishnerovitz formula, now we can give some application of this formula. So I'm going to start with a theorem of Lishnerovitz. So if you have a Riemannian manifold which is compact, spin, so I'm going to limit myself to the spin case at least for the first two theorems. Then later on I will give more application for spin C manifolds or for spin C structures, and maybe the generalization of some results from spin to the spin C case. So compact spin with strictly positive scalar curvature, then the kernel of the Dirac operator is trivial. 2, if you take any eigenvalue lambda, the satisfies lambda squared strictly bigger than 1 over 4 the infimum of the scalar curvature. So I'm going to prove these 2 points. Proof. Of course, these 2 points are direct application of the Schrödinger-Lishnerovitz formula. So if you take the Schrödinger-Lishnerovitz formula applied to any spinor, to any non-trivial spinor psi, we have d squared psi lambda plus 1 over 4 scalar curvature of psi. Now try to integrate over m. try to take the scalar product with psi, then integrate over m. So you get the Laplacian of psi plus 1 over 4 the integral scalar curvature of normal psi squared. But D is forming self-adjoint, so this is d psi norm squared, and the Laplacian of psi is the norm of nabla psi squared plus 1 over 4 the scalar curvature psi. And of course this quantity here is positive or 0, and it's non-negative if you want, and this quantity here is strictly positive. It means d psi cannot be 0 for any non-zero, non-trivial spinor psi, so the kernel of the Dirac operator is trivial. Now let's prove the Leash-Horowitz inequality. So take lambda eigenvalue of D, and d psi is lambda psi, so psi is the corresponding eigenspinor. So again, taking the same integral inequality that I used in the first part, d psi squared scalar curvature psi squared is integral of nabla psi squared, but again this quantity here is positive, and d psi squared is lambda squared norm of psi squared, and this will give that lambda squared is strictly bigger or equal to 1 over 4 the infimum of the scalar curvature. However, equality cannot be attained, because if lambda squared is equal to 1 over 4 the infimum of the scalar curvature, then from the previous slide the integral of nabla psi squared should be 0, and this implies that nabla psi is 0. If nabla psi is 0, so d psi is 0, and psi, since psi is an eigenspinor, so it's a non-trivial spinor field, so the kernel of the Dirac operator is not trivial, which give a contradiction. Hence, the inequality is strict, 1 over 4 the infimum of the scalar curvature. The first direct application of the Leash-Horowitz inequality is the following topological abstraction for the existence of positive scalar curvature metric. In fact, if you have a Riemannian manifold which is spin and compact and with positive scalar curvature, let's take n to be 2k, so n is even. We know that the index of the positive part of the Dirac operator is a dimension of the kernel of the Dirac operator d plus minus the dimension of the kernel of the Dirac operator d minus. So what are the d plus and the d minus? In the even case, I didn't show it yet, but I will do it later on. The Dirac operator of the spinor bundle can be split into positive spinors and negative spinors, and then the Dirac operator the Dirac operator acting on the positive spinors will be called d plus, and the one acting on the negative spinor will be called d minus. But d plus and d minus have both kernel 0, so you get that the analytic index, that's why I should maybe write here A, the analytic index of the d plus is 0, but by the Atiyah-Finger index theorem, this analytic index is equal to the topological index, which means that the topological index is 0, and hence it yields a topological obstruction for the existence of positive scalar curvature metric. So this gives an obstruction a topological obstruction for the existence of positive scalar curvature matrix. In 1985, Friedrich improved the Leash-Horowitz inequality and proved the following for theorem by Thomas Friedrich. So you have a Riemannian manifold which is compact and spin. So any eigenvalue lambda of D satisfies lambda squared is bigger than or equal to n over 4 n minus 1 when n is the dimension of the manifold, the infimum of the scalar curvature. Of course, needless to mention that it improves the Friedrich inequality because n over n minus 1 is strictly bigger than 1, so you get bigger than 1 over 4, strictly the infimum of the scalar curvature, which means that it improves the Friedrich inequality. Much more than that, equality is characterized by the existence of a real killing spinner So what does it mean, a real killing spinner? A psi, it's a spinner satisfied that the covariant derivative is proportional to the Clifford multiplication gamma x of psi up to a constant. In my case, it's minus lambda over n, where lambda is the eigenvalue. And equality also implies that your manifold M is Einstein. So the existence of special killing spinners or a special spinner field like the one of the killing spinner implies automatically that your manifold is Einstein manifold. So that's why, as I said in the first day on Monday, that the existence of a special spinner field on a manifold play an important role on the geometry of the manifold and the topology as well. For example, here the existence of a killing spinner will automatically imply that the manifold is Einstein. I'm going to prove the Friedrich inequality, and I will try to characterize the equality case and prove that in such case your manifold is Einstein. Okay, so let's make the proof. So of course, again, in the proof is based on the Leash-Horowitz or on the Schrödinger-Leash-Horowitz formula. So first of all, you take any spinner fields, try to calculate deep psi squared. This is the norm of sigma gamma ei nabla ei of psi squared I from 1 to n, which is of course less or equal than sigma gamma ei nabla ei psi squared. But we know that gamma ei squared is gamma ei, which is minus 1. Of course, so and square it, you get 1. So it's equal to sigma from 1 to n 1 nabla ei of psi and everything is squared. And now you apply the Cauchy-Schwarz inequality to get, so the Cauchy-Schwarz inequality here you get n sigma nabla ei of psi squared, which is of course n nabla psi squared. So in total, deep psi is less or equal than n nabla psi square. And now let's use again the Schrödinger formula. So by the Schrödinger formula, we have 1 over the integral of 1 over n deep psi square is less or equal than the integral of nabla psi square. It comes from the previous inequality. And now let's apply the Schrödinger formula. Nabla psi squared integral is the integral of deep psi square minus 1 over 4 integral of scalar curvature by norm of psi square. And this is true for any eigenspinor, it's true for any spinor field psi. So let's combine these two terms to get 1 minus 1 over n integral of deep psi square is bigger than 1 over 4 the scalar curvature norm of psi square. And in the special case, when for deep psi equal lambda psi, so this will be lambda squared norm of psi squared, you will get lambda squared integral of norm of psi squared bigger or equal to 1 over 4 and n minus 1, the integral of the scalar curvature, which is bigger or equal to n of 4 n minus 1, the infimum of the scalar curvature integral of norm of psi squared. But since psi is an eigenspinor, of course it's non-zero, or it's not trivial eigenspinor. It's not a trivial spinor field. So let's simplify by integral of norm of psi squared to get lambda squared bigger or equal n over 4 n minus 1, the infimum of the scalar curvature, which is the Friedrich inequality. Let's try to characterize first the limiting case or the equality case. Assume that lambda squared is equal to n over 4 n minus 1, the infimum of the scalar curvature. So if equality holds, then all the previous inequalities should be equalities. So by the Cauchy-Schwarz characterization in the equality case, we should have gamma ei nabla ei psi should be equal to gamma ej nabla ej psi for all I j between 1 and n. And so this means deep psi, which is sigma gamma ei nabla ei psi, since all these terms are equal, it's n gamma ei nabla ei psi. Try to multiply Clifford multiply both sides by gamma ei to get gamma ei deep psi is n gamma ei Clifford gamma ei, this is minus 1 nabla ei psi, or if you want you can write it as nabla ei psi plus 1 over n gamma ei deep psi is 0. But don't forget that psi is an eigenspinor. This is lambda n, so this is lambda psi, so I get nabla ei psi plus 1 over n gamma ei. Deep psi is lambda psi 0, which is nabla ei psi minus lambda over n gamma ei of psi, and this is the killing equation or a killing spinor field. Much more than that, psi satisfies also from the previous slide, if you want, it satisfies the following twistor equation. But of course, because psi is an eigenspinor, this will be reduced to the following Killing equation given by nabla AI psi is minus lambda and gamma AI psi. Now the opposite is also true, or the converse is also true. It means, having assumed that I have nabla x, I have a spinor field, a killing spinor field given by nabla x psi is, I don't know, f gamma x psi I don't know what's happening. My screen was not showing, so I'm going to repeat. So if in the case of I have an equality, in the Friedrich inequality, I'm going to get the killing spinor, and now I'm going to prove the opposite, the converse. So if I have a killing spinor, then I have equality, the equality case in the Friedrich inequality. So and at the same time, I'm going to prove also that my manifold is Einstein. So assume that my manifold has a killing spinor. So nabla x psi plus some f over n x gamma x of psi equal to 0. So where here f is a real function, so I'm going to do it much more general. I'm going to assume that my f is a function, what we call a generalized killing spinor, and I'm going to prove in fact that f is constant and equal to and this will be the eigenvalue lambda, and psi will be the eigenspinor corresponding to the eigenvalue lambda. So we will prove that M is Einstein and F is constant, or much more, and F squared is n over 4 n minus 1, because I don't need to write the infimum of the scalar curvature because my manifold is Einstein, so the scalar curvature is already constant, so scalar curvature here. So this means that I have the equality case in the Friedrich inequality, and my manifold is of course Einstein. I'm going to do it. So because psi satisfy nabla x psi equal minus f over n gamma x psi, or gamma y, let's write it y here as well. So one can calculate nabla x, nabla y of psi to get minus 1 over n x of f gamma y of psi minus f over n gamma y nabla x psi minus f over n gamma nabla xy of psi. So you just use the property of the connection lambda and the compatibility equations, which is minus 1 over n x of f gamma y psi plus, let's replace the quantity here by the killing equation, plus f squared over n squared gamma y gamma x psi, and of course the last quantity minus f over n gamma nabla xy psi. In a similar way, one can calculate nabla y nabla xy psi, to get minus 1 over n gamma x psi plus f squared over n squared gamma x gamma y psi minus f over n. In a similar way, nabla yx psi. Of course, we have calculated here nabla x, nabla y, nabla x of psi, and nabla x, nabla y of psi. So I can conclude with the spinorial curvature xy of psi to be nabla x, nabla y psi, minus nabla y, nabla x psi, minus nabla the bracket of psi, to get both combined minus 1 over n x of f, y minus y of f x, Clifford psi, plus f squared over n squared gamma y gamma x minus gamma x gamma y of psi. Of course, here I calculated the spinorial curvature, and using the local expression of the spinorial curvature, one can also prove, we can easily prove the following Ricci identity: minus half Ricci x Clifford multiplication with psi is sigma I from 1 to n gamma ei, the spinorial curvature xei of psi. So I'm not going to prove this identity, but you have just to use the local expression of the spinorial curvature, then multiply Clifford multiply by gamma ei, then sum over it to get the Ricci curvature, Clifford the spinor field psi. And now I can replace the spinorial curvature here by the quantity found for the generalized Killing equation to get minus 1 over n sigma over I x of f gamma ei Clifford gamma ei psi minus ei of f gamma ei gamma x of psi. This is for the first sum, plus f squared over n squared sigma, of course, over I, gamma ei gamma x minus gamma ei gamma x gamma ei psi. So I just choose here from the previous slide that the Riemannian or the spinorial curvature or the spinorial tensor is given by the following quantity, and I replace it in my next slide for y equal ei, and hence we can use the fact that gamma ei is minus 1, and also we can use the fact that gamma ei gamma x gamma ei sigma is, so using the fact, I'm going to write it here, that sigma gamma ei gamma x, it's a simple calculation using the property of the Clifford multiplication, is n minus 2 gamma x. So I will get minus half the Clifford multiplication of Ricci x psi is equal to again minus 1 over n minus nxf psi minus gamma df gamma x psi plus, of course, f squared over n squared minus n gamma x minus n minus 2 gamma x psi. And after simplification, this is x of f psi plus 1 over n gamma df gamma x psi minus 2n minus 1 n squared f squared gamma x psi. Of course, where I combine the following terms of gamma x, I kept this term alone and this one as well. this is true for any vector x, so don't forget this is minus half Ricci x Clifford psi, and this is true for any x. So maybe I should write it here, minus half, or maybe here. So this is minus half gamma Ricci of x epsilon. Now in the particular, this is true for any vector x, and in the particular case, if you take x to be your df, what you will have, so you will get minus half Ricci of x gamma psi plus 2 n minus 1 n squared f squared gamma of x psi equal x of f psi plus 1 over n gamma df gamma x psi, and as I said, by taking x to be df, so what you are going to get here, this is df squared, and here gamma df, so this is a property of the Clifford multiplication. You are going to get the norm of df squared, so this is 1 minus 1 over n df norm of df by psi. And now I will avoid writing one more time. Take the scalar product of this quantity with psi, you will get the following. And of course, as you can see, this part of the equality is real, and this part of the equality is imaginary. Of course, we always have, for any vector x, gamma x psi is always imaginary. So this part here is real, and because I have the Ricci x Clifford psi and here x Clifford psi, though this part is imaginary. Conclusion, both quantities should be 0. So as a conclusion, if this quantity here in yellow is 0 and then psi is a non-trivial spinor, I'm going to get df squared 0. This means that df is 0, automatically f is constant. So f is constant, and then come back, since f is constant, so we come back to this identity here, which is true for for this one, which is true for any x, to get, so let's write it again with f is constant, to get x of f minus 1 Ricci gamma of Ricci x psi plus 2 n minus 1 gamma x psi. This is identically 0. Now, of course, because my spinor field is non-trivial, one can conclude that Ricci x is 4 n minus 1 n squared f squared by x. So this implies that my manifold is Einstein, and because it is Einstein, this quantity here, or this constant here, will be equal to the scalar curvature over the dimension. And we get that f squared is scalar curvature n over 4 n minus 1. So this is the existence of a generalized Killing spinor, so much more than being a constant for any f. F should be constant. It should be equal to n over 4 n minus 1 scalar curvature. My manifold is Einstein. That's why the scalar curvature here is without nth, if you want. So here I'm going to finish with the last remark. So the existence of Killing spinner, of real Killing spinners, of course, characterizes the equality case in the Friedrich inequality, which is characterized also by the manifold M being the sphere, but only in some dimension. This was proven by many authors, Usama Ijazi, Andrei Moriano, etc. So the sphere characterized the equality case in the Friedrich inequality. So of course the sphere with the Euclidean metric have Killing spinners, of course, but this is only in some low dimensions and some specific dimension. So it means that the existence of Killing spinners does not imply that the manifold is necessarily Einstein or necessarily the sphere. There are in some dimension, other examples than the sphere where the manifold has a Killing spinner and it is not the sphere, of course. But this is not my goal in this mini course, so I'm going to skip the proof of the following fact. Maybe now you are asking what will happen if I move from spin to spin C. So what will happen with the Friedrich inequality? So under the same condition, if you have a manifold, but now spin C, compact, then the first any eigenvalues of the spin C Dirac operator is bigger or equal to n over 4n minus 1, the infimum of the scalar curvature, minus Cn, the norm of the curvature 2 form of the connection associated with the auxiliary line bundle defining the spin C structure, where Cn here is the following constant to the integer part of n over 2, the square root of the integer part of n over 2, and of course the norm of omega is with respect to the metric G of my manifold. And equality case is characterized, as in the spin case, by the existence of a Killing spinner so it means that you have nabla x psi minus lambda n gamma x psi, but of course here the nabla is the spin C connection instead of the spin connection, because I have a connection now on the auxiliary line bundle. So I have the curvature term, and plus this Killing spinner, we have a control on the auxiliary on the curvature 2 form of the auxiliary line bundle, and the Clifford multiplication of the 2 form is proportional to its norm. So ICN over 2, of course, norm of omega psi. So in somehow we know what is the Clifford multiplication of the 2 form omega on the eigenspinner psi. It's proportional to the norm of the 2 form omega. Of course, omega is any 2 form, the curvature of the connection that we equip with the auxiliary line bundle, or the one form, the imaginary one form as a connection on the auxiliary line bundle. If you remember, we denoted by I alpha, and omega is its curvature. And this equality, of course, does not give that my manifold M is Einstein in general. So that's a of course, because if you remember, when we use the Ricci identity and the Schrodinger formula, there exists this extra term on omega, which is the curvature again of the auxiliary line bundle, that we don't have any control on it. So my manifold is not in general Einstein. However, Andrei Morianu classified spin C structures, of course, on simply connected complete manifolds, having a killing spin C spinner without this extra condition on the curvature, on the Clifford multiplication of the curvature to form on the spinner. And he got that Sasaki manifolds, for example, admit a spin C structure with killing spinner. And as you know, Sasaki manifolds are not in general Einstein. So not all examples of killing spin C spinners imply that my manifold is Einstein. So example of manifolds, spin C manifolds with killing spinners or Sasaki manifold. For example, the Berger sphere, any Sasaki manifold also has a killing spinner. So I'm going to stop here for today. Tomorrow we are going to describe or to see how we can restrict a spin C structure, the Dirac operator, any killing or spinner or whatsoever, all these ingredients, how we can restrict it from a manifold M to its hypersurfaces, and how we can deal with the Dirac operator on my manifold and the hypersurface. What is the relation between both Dirac operator, to see later on how we can give much more geometric applications. And now just to tell you that the proof for the Friedrich spin C inequality is very similar to the case of the spin case. I mean, you need to use the Schrodinger-Leshravis formula to get the Ricci identity, to have control on the auxiliary, on the curvature to form of the auxiliary line bundle, and that's it. See you